Okay, so let's take a look at section 11.1. And in this section, we're going to be testing claims about two population proportions. So I'll just say testing claims comparing, this time, two population proportions. Now, at the appropriate time, after we get through chapter 11, I'll give you another sheet like this, and it'll compare all three methods from chapter 11. And you'll see how they're similar, and then how they're different. So here's the idea. We have two populations, population 1 and population 2. And what we're going to do is we're going to take a sample from population 1 and a sample from population 2. Since we're comparing proportions, from this sample, we're going to identify X1 and N1. We can't just say X and N because we're going to have two sets of X's and two sets of N's. And this one, from the sample, we're going to write down X2 and N2. These two sample sizes do not need to be the same, but if we're going to use a normal sampling distribution, then you have to have N1, P1, Q1 larger than 10, and N2, P2, Q2 larger than 10. So you need them both. Then what we're going to do is, to see if there's a difference, we're going to compare P1 with P2. And P1 is found by calculating the sample proportion of the first sample statistics in the same way that we've normally calculated it. And then P2 is X2 over N2. So what we're going to do is we're going to compare these two to see if there's a statistically significant difference. Now we can compare them to see if there's a difference, and then we'll do the statistics or run the hypothesis test to see if there's a statistically significant difference, not just a difference that we can observe. So here's the test, and let me go through the 5 steps, and then we'll look at some problems. All right, so step 1 is always to write the hypotheses, and as before, we have 2 hypotheses, so that's not different. And also, as before, we have 3 different types of tests. We have the one-tailed left, one-tailed right, and the two-tailed test. And it depends on whether someone's going to be making a claim that the two population proportions are not the same, or if one's greater than the other, or if one is less than the other. So if we do the one-tailed left test like this, the alternative is going to be P1 is less than P2. And the null hypothesis is always no difference. So in this case, if we're looking at and comparing two population proportions, no difference means that they're the same. In fact, in all 3 versions, we're going to assume that the two population proportions are the same. We've got the left test, the left-tailed test, the right-tailed test, where we use the greater than sign, and then we have the two-tailed test, where you have area on both the left and the right. And here's where we use the not equal to sign. So two-tailed test, this is similar to the test that we've done in the past. This is a right, because the area is to the right, right-tailed test. And to determine right-tailed, left-tailed, two-tailed, you just focus in on that sign in the alternative hypothesis. So there's no difference here from what we've done before. You can see the hypotheses are different, but there's no P0 value here. We're not going to have a P0 that corresponds to P1 and a P0 that corresponds to P2. Because here what we're doing is we're just looking at the difference between the two. All right, so those are the hypotheses. And what's nice about this, since you don't have to search for the P0 value, these hypotheses, one of these 3 you will use in every single hypothesis test in this section, because you're always going to be comparing two population proportions in some way. All right, so step 2, that's the one where we identify the level of significance. And it turns out that this is no different than what we've done in the past. So they'll either give you the level of significance in the problem. If they don't, then we'll just assume that it's 0.05. Probability of making a type 1 error is 1 in 20. We want the probability of making an error to be a very small number. So step 1, step 2. You can see the similarities there, differences in what we've done in the past. All right, where most of these tests are going to differ is going to be on that step 3. So the step 3 is where we gather the evidence. But in every one of our tests, to gather the evidence, most of the time, that means calculate the test statistic and calculate the p-value. It turns out that the test statistic in this case is also a z, and then the p-value is going to be based on that test statistic. So these two numbers are linked. If you wanted to draw them in a picture, if this is your z sub 0 value, this would be the p-value for a one-tailed left test. Now this test statistic can be, in a lot of different places. If it happened to be here, then we would shade everything to the left of this value. There's a classical approach for this one. So we can do identify this classical graph that we have here, where we identify the reject region and do not reject region. And there's also a p-value approach. All right, so here's the test statistic. Now remember, we're comparing two proportions. So we're going to have two sets of sample statistics, x1 and n1, p1 hat. So if there's a difference, so what we usually would do is, well, let me kind of go over here and say, in the old case, when we looked at the test statistic for a sample proportion, it looked like this. We have the sample result here and what we're assuming the population to be here, and then divided by the standard error. Now, we haven't talked about a standard error in a distribution where we have two population proportions, so I have to give that to you. So it was sample results minus assumed population result divided by the standard error, which is this guy. So that format will be pretty much the same. But here's what the test statistic will look like. And I'm just going to try to draw an analogy between what we did before. You have the sample results, but instead of subtracting the p-hat minus the single population proportion, to make this test statistic larger, we're going to actually subtract the two sample proportions. If there's a big difference between the sample proportions, then the z value will be big because this difference will be big. All right, and then we subtract the similar population, well, p1 minus p2, if we happen to know what those are. We don't know what those are, but in our null hypothesis, we were assuming that p1 is equal to p2. And if p1 is equal to p2, and we subtract them here, this whole piece of the formula is equal to 0. So it's not really needed. So a lot of times you don't even see this piece. And the only thing that appears on the top is p1 hat minus p2 hat. Then we divide by the standard error. All right, but the standard error term involves two proportions. And let me just go ahead and give it to you. We're not really going to use it a whole lot, but this is p hat times q hat, which is 1 minus p hat. And then we, well, you can put them together or not. 1 over n1 plus 1 over n2. All right, now p hat here is what we're going to be calling the pooled proportion, or the pooled sample proportion. And what you do to get that is you add up the x's of the two samples and divide by the sum of the n's. And that number is going to be somewhere between p1 hat and p2 hat, or if we assume that p1 is less than p2. It could be p2 here and p1 hat, but the pooled proportion will be between these other two. So the formulas you can see are getting a little bit more complicated. And that's why we rely on the calculator function to crunch these out for us. The distribution is the z distribution. So we can use the inverse norm to find the critical values as before, and we'll be using the normal CDF to calculate the p-value if we calculated it by hand. All right, so let me go right to the calculator function here. Since now we have two proportions, so you're going to look for two proportions. The distribution is still the z distribution, z critical value there, z distribution, and then followed by the word test. Now, when we did the one prop z test, we needed to specify p0. And this was the number in the null hypothesis. However, in this particular test, our null hypothesis is always the same. P1 is equal to P2. So the calculator function is not going to require this first step. There's not going to be a changing number in every test. It's always P1 equals P2. So there's no need to ask any information about the null hypothesis. So, but we do know, what we do need is X1, N1. That's from our first sample. And then X2, N2. That's from our second sample. And then the calculator then could calculate P1 hat, which is just X1 over N1. And the calculator can also use these next two numbers to calculate P2 hat. And it needs these guys in order to calculate the test statistic up here. So if you give it X1 and N1, X2 and N2, then it has what it needs to calculate all this. In fact, if you look down here, the pooled proportion is this number. And so as long as you give it X1, X2, N1, N2, all of these numbers, it can calculate this. And if it can calculate this, P hat, then you can use it here and you've got everything you need. So this is the only thing that you need to feed the calculator. Just those two sample sets of sample statistics here. You do have to specify down here, this is information about the alternative. And since the alternative hypothesis can change from the less than to the greater than to the not equal to, down here, you're going to be given these three options: not equal to P2, less than P2, or greater than P2. And you have to specify the correct one. And this is similar to what we've done in the past. All right, so that's what I want to say about step 3. And you'll see as we go into some more examples how things are going to change a little bit. Step 4 is to make the decision. You're going to see as we move forward, we're probably primarily going to make the decision based on the p-value approach. So if p is less than alpha, reject, and if p is greater than or equal to alpha, do not. You can also use the classical approach if the test statistic falls in the critical region, the do not or the reject region, then you reject the null hypothesis. And then we will interpret the conclusion in a similar way as we've done before. So we're going to go back to this one as well. And the hypotheses will look different, but the way we start out the wording will be the same. All right, so you have some notes to read. You do need the two samples to be independent. Knowledge of one group gives you no information about the other, probability of the other. So we have to make sure that we have independent groups. They give you some information here about this pooled proportion. They give you some information here about the standard error term. Here they say that N1 times P1 times Q1 must be larger than 10. And N2, P2, Q2 must be larger than 10. Then you have this similar criteria that you have to have a small enough sample size. Otherwise, you lose the independence criteria. Here are your three tests: two-tailed, left-tailed, right-tailed. There is a classical approach. Here's the test statistic. They give you the pooled proportion there. We're going to be using the calculator function for the most part. Make the decision and then state the conclusion. All right, let's take a look at a couple of examples. And what we'll do is, we'll answer their questions, but we'll go through the 5 steps. So the first one is number 19 on the handout there. Abstaining from alcohol. In October, okay, going way back to 1947, the Gallup polls were around back then. And so here's my picture, 1947. I take a sample. And then from this sample, they surveyed 1,100 adults and asked, are you a total abstainer from, or do you on occasion consume alcoholic beverages? So do you drink alcohol or not? Of those, 407 indicated that they were total abstainers, did not drink. All right, let's calculate the sample proportion way back when. We're going to call these X1. So this would be our first group, way back when. X1 divided by N1. All right, so back then, 407 divided by 1,100 is 0.9. So 37 did not drink at all. All right, In a recent survey, the same question was asked 1,100 Americans, and 333 said they were total abstainers. Okay, so it doesn't say current year, so I'll just say 2020. We take a sample, and we find that 333 out of the 1,100. So if you calculate P2 hat and take X2 divided by N2, you can convert that rate into a percentage if you like, or just compare it as a decimal, and it turns out to be 0.303, so 30.3%. So we observe a difference here. Back in 1947, it appears that there was a higher percentage of abstainers, people who did not drink, than in today, where it's only 30.3. Now, our job as a statistician is to decide if this difference that we observe here, if it's statistically significant. Is it enough difference in order for us to claim that, well, whatever the claim is, but it looks like from the sample here that the claim is going to be that fewer people abstain these days, which means more people drink on average these days. We can see that, but is that difference statistically significant? And that's why we have to run the test, because it could very well be that this difference that we observed is based on just kind of the random sampling variation that we'll experience when we take a single sample. All right, let's read the rest of it. It says, has the proportion of adult Americans who totally abstain changed? Okay, so when they say changed here, they're not telling you how it changed. If they wanted to say that the percentage increase of abstainers, then they would say, has the proportion of adult Americans who totally abstain from alcohol increased? Or they could say decreased. But here they just said changed, so they didn't commit to one way or the other. So changed, you're going to be using not equal to. There's no mention of increase or decrease. Okay, and then the other thing it gives us is alpha, the significance level, 0.05. Has the proportion of American adults who totally abstain from alcohol changed? Okay, so here's where you would have kind of a bunch of steps where you would be asked to go through the hypothesis test. So the first one is to write the hypotheses. What's nice about this section is that the null hypothesis will always be the same. What's more difficult about this problem is that we now have two variables in our hypothesis. And so we need to define them both. It's very important that you do it in this case because we need to know which one's talking about 1947 and which one's talking about the current year. So proportion that abstain in 1947. I'm kind of writing the bare minimum of how you would define these variables. P2, proportion that abstain from alcohol in the year, well, in a recent year, we'll call it 2020. All right, and then the alternative, it's going to be a two-tailed test because they didn't indicate whether they think the number or the percentage of abstainers increased or decreased. They said has changed. Let me read it one more time. Has the proportion totally abstain changed? All right, so what we're going to say is when we turn this around to a claim, is we're going to say the claim is that the proportion has changed. They asked the question, did it change? We're going to write our hypotheses so that it did change. And what that means is that we're going to write the word claim next to the alternative. The alternative is generally the research hypothesis. This is what the researcher wants to show, that there in fact has been a change. We know from our sample results, if there has been a change, the percentage of abstainers has decreased. And that means more people these days are drinking some alcohol. Okay, define the variable. Or maybe I'll just, instead of A, B, C, I'll just label them as the steps. Step 1. Step 2 was done for us. Alpha equals 0.05, but you still have to write it out. That's the level of significance. Okay, for step 3, we do have the classical approach and the p-value approach. The p-value approach is always the easiest one because the calculator will crunch the numbers for us. So if you're going to use the p-value approach, then in this case, you're going to use the two-prop z-test. All right, so let's see what that would look like. Again, to go there, you want to hit the stat key And then all of the tests will be in the test menu of the stat key. And you can see that 2-prop z-test comes up pretty quickly. It's option number 6. All right, so I'm going to type in the numbers that we have up here. We label them exactly as we're going to enter them into the calculator. So for X1, 407 back in 1947 said that they never drink. They abstain always. 1100 is the N1. All right, we're going to move over here. The X2 is 333, and the N2 is also 1100. Doesn't have to be. Notice there's no place up to the top for some P0 or some P10 or P20 because we don't need to have any information about the null hypothesis because it's always the same. P1 equals P2. But we do have to give it information about the alternative hypothesis because the calculator needs to know when calculating p-value if we're dealing with a one-tailed right, one-tailed left, or a two-tailed test. So we have to select the not equal to icon to match. P1 not equal to P2. That's exactly what it says here. And then it's going to calculate, and the two things it calculates is are the test statistic and the p-value. So we'll just write those down. And here it is. Notice it says Z. And we use the standard normal again for proportions. It's 3.3 standard deviations away from the mean, and we know that that's unusual in a Z distribution. So you can see this p-value is tiny. This is another one of those p-values that you got to read it from right to left because you can see over to the right side of that problem, it's times 10 to the negative 4. P-value will always be a number between 0 and 1. You'll notice also the output. It'll give you P1 hat and then P2 hat, and then it gives you that pooled proportion right there. And notice the pooled proportion is somewhere between 0.1 or P1 and P2. In this case, it'll be directly between P1 and P2 because the sample sizes for the two samples are the same. If you scroll down further, it'll give you more information. Just reports back your N. Okay, so this is 333, and N2 is also 1100. And then P1 not equal to P2. And this gives us Z, this is the test statistic, equal to 3.339, and P, which is p-value, not to be confused with the other P's that you're going to see in this problem, is equal to, all right, I'm going to write it down just so you get in the habit of reading these problems from right to left. So we're going to move this decimal point 4 places to the left. 1, 2, 3, 4. So if you were to write it in general form, non-scientific notation form, you can see it's tiny. Sometimes an error that students will make, they'll say, oh, P is 8.4. That's larger than 0.05. And so we do not reject the null hypothesis. And that's exactly the opposite decision you want to make here. So get comfortable with the way that the calculator reports the p-value. All right, while we're here, well, what I might do is just say step 4, we are going to reject the null hypothesis since p is less than alpha. We calculated p to be this 0.0008 number here, and alpha was given to us as our line in the sand, level of significance. And you can see this number is less than this number, therefore P is less than alpha. And if P is less than alpha, the decision is to reject the null hypothesis. And then step 5 is to write the conclusion or interpret the conclusion. So you might want to refer to that 2x2 grid that I gave you earlier until you get it right. But we are going to reject the null hypothesis, which means we have support for the alternative, which is the claim. So we want to say there's evidence to support the claim. So this observed difference that we saw up here, 37% to 30.3%, it is in fact statistically significant. So there is evidence to support the claim, and then you have to state in layman's term what the claim was. The claim was that the proportion who abstain these days, or back in 1947, it was different. And so we're going to state our conclusion based on what we are showing support for. So the percentage that abstained back in 1947 is different than the percentage that abstains in 2020. I'll just call them non-drinkers, non-alcohol drinkers, is different than in a recent year. And I'll just call it 2020 or something like that. You want to be sure that you report out the results so that someone who's unfamiliar with stats, they know what the evidence showed in this case. The classical approach here is very much like the classical approach from earlier. One-tailed test, two-tailed test. So one-tailed test is a left test or a right test for this one. And you're correct, two-tailed test. So we're going to draw it as such, two-tailed test. There'll be a little bit of the, or half of the alpha in the left tail, half of the alpha in the right tail. And since alpha is equal to 0.05, we're going to divide it in two and put half of it over in the left and half of it over in the right. Now, the way that you describe the regions is identical to the way that you described them for the one-tailed or for the one sample test that we've done. Away from the middle is where we're going to reject the null hypothesis. So we've got two reject regions and a two-tailed test. In the middle, when the difference is close to zero, we're not going to reject. So what we're actually plotting here is a bunch of P1 minus P2 hats. And so instead of just a P1 hat that we plot here, we're going to be looking at the differences. And we plot all those differences. If the difference falls over here, that means there's a big difference between P1 and P2. P1 is much smaller than P2. And if we get a test statistic over here, that means that P1 is significantly larger than P2. In here, they're too close. Okay, now this is a Z distribution. And so these are the Z critical values. So this one is going to be Z of alpha over 2, the two-tailed test, and we use the inverse norm of 0.025, 0 and 1, and this is a number that you will recognize, negative 1.96, and the other one over here is 1.96. By symmetry, zero's in the middle. And finally, to complete the classical approach, we have our test statistic, 3.339, and we're going to plot that. It's 0, 1, 2, 3, and a little bit. So 3.339, that's our test statistic. It also gets plotted on the horizontal scale. And you can see because of where we plotted it, it falls out here, falls over in this region here. So that's the reject region. So the decision is going to be the same. Reject the null hypothesis. So yeah, it's quite different. It seems to be more people are drinking these days, according to these results. All right, so the way that we interpret a confidence interval in this case is a little bit different. So let me show you how that works. So what does a confidence interval mean in this case for section 11.1? Well, remember that confidence intervals allows us to estimate something. Back in chapter 10, we were estimating a population mean or estimating a population proportion. In this situation where we have two groups, we're going to estimate P1 minus P2. So that's what we're estimating here. Now, three things can happen. First, if P1 minus P2 is less than 0, so up here I'll say the sign of P1 minus P2. The confidence interval is an interval of numbers, right, like this. And if your entire interval here is negative, that means you have a negative here and a negative here. And if you're going to estimate P1 minus P2 and you get a negative and a negative, that's going to be evidence that P1 minus P2 is less than 0. And if P1 minus P2 is less than 0, then if you add P2 to both sides algebraically, you get P1 is less than P2. And if we find that P1 is less than P2, then that's going to give you evidence to support the alternative hypothesis, because only the alternative hypothesis would contain the less than. All right, two more situations. If P1 minus P2 is greater than 0, that is, you're estimating this and you find a confidence interval that looks like this, where both numbers are positive. So we're estimating P1 minus P2, and we find that this is how we estimate it with an interval. Well, every number in this interval is positive, So P1 minus P2 is positive. And then if you add P2 to both sides, you get P1 is greater than P2. So if you see a positive confidence interval, that means that P1 is larger than P2. That also gives us evidence to support the alternative hypothesis. Because greater than, the only place you're going to see greater than is in the alternative. The third scenario is if you calculate a confidence interval and you see that the lower bound is negative and the upper bound is positive. Well, that means that zero is in the middle somewhere of that interval. So this could quite plausibly be the case that P1 minus P2 is equal to zero because zero is in this interval. In which case P1 is equal to P2 if you solve this algebraically. And if P1 is equal to P2, that's precisely what our alternative hypothesis says. I mean, our null hypothesis says. So in this case, you would find support for, all right, now we have a calculator function that will calculate that confidence interval for us. And we're dealing with two proportions. We're using a z distribution. And if you want to calculate an interval, then int. And there's the calculator function that you want. So let's go back to this example here and type in everything that we need to calculate a confidence interval in this context. All right, so we're going to go to stat, over to tests, and you want the 2 prop z int. So it's not option 6 here because this is what it would give you for the hypothesis test. It is option B, 2 prop z int. Notice it's going to ask you for the same 4 numbers that you were asked for in the earlier one. X1 is equal to 407. N1 is equal to 1100. X2 is equal to 333. And N2 is equal to 1100. And then if it is a confidence interval, it's going to ask you for the confidence level. And so let's say that this corresponds to the same thing that we found earlier. If we let alpha be 0.05, then the C level is going to be 0.95. And then let's calculate and write down the interval. Now, you don't really need to focus in on these numbers specifically, but you do need to focus in on whether they're positive or negative. And so in this example, we have a positive number on the lower end and a positive number on the upper end. So 2 positives. So if we're estimating P1 minus P2, since the whole interval is positive, we know that positive means greater than 0. So this gives us evidence that P1 minus P2 is greater than 0. And if P1 minus P2 is greater than 0, that means we have evidence to support that the proportion back then is greater than the proportion today. And this is support for the alternative hypothesis. So P1 minus P2 greater than 0, that's this one here, where you're going to get 2 positives. And that's support for H1. All right, and so that's what all of this is. Again, you have to have these requirements to ensure independence and to ensure that you have a large enough sample size so that your sampling distribution is a z distribution. You can see this mess of a confidence interval formula. This would just be the lower bound, and then a comma, and then this would be the upper bound to get the right limit. All right, and here's the calculator function. You can see it here. I don't know if it's option number 6, but I think it was, in fact, the 2 prop z test. And then if you're going to do confidence intervals, 2 prop z int. So they're very closely related, just depends on which one you're using. All right, there's one last result, and this one is similar to what we did with confidence intervals back when we said, you know, what sample size should we use so that the margin of error would be equal to this amount? And you do have a formula for that. You can see it's very similar to what we've had in the past for a proportion. And the way that this works is that once you find the sample size, you're going to use the same sample size for the first group as you use for the second group. So the sample sizes will be the same. And they're equal to a half times the critical value divided by the margin of error squared. And you're always going to round up. So let's look at one example here. in the couple of minutes we have left. An educator wants to determine the difference between the proportion of males and females who've completed 4 or more years of college. What sample size should be attained? Same sample size for men as women. If the estimate to be within 2 percentage points, okay? 2 percentage points. So plus or minus 0.02. So the margin of error is 0.02. That's the number that you type into this formula right here for E. What sample size should be attained if she wishes to estimate within 2 percentage points with the 90%? All right, so the C level is equal to 0.90. That's going to help us find the critical values. All right, so from here, you do inverse norm. If 90% is in the middle, then 10% is on the outside, which makes 5% in each tail. All right, so the C level is going to be plus or minus 1.645. This is the same one that you found in that practice problem. Okay, so we have this here. If we don't have a previous P1 and P hat, we're just going to use P5, and if we do, then we're going to use this one here. So in part A, and I'm kind of out of time here, so I'll finish this up and put it in the notes so that you can see it. If you want to stay around, you can stay around and write this down as well. All right, so what they give you is they give you the male, the P1 hat is equal to 0.275, and then they give you the P2 hat, which is 0.231. So for the first one, the N is going to be equal to P1 hat Q1 hat plus P2 hat Q2 hat times this piece here. So we're going to have 0.275 times, all right, 1 minus that. And 1 minus that is 0.725 plus, and we're going to go to the P2, 0.231, and then 1 minus that, 0.769. All right, so we're going to add those two together, and then we're going to multiply by the 1.645 over the 0.02, and we're going to square that. And whatever we get, we're going to round up. If she does not have any prior estimates, then N is going to be just 0.5 times this number. And then from here on out, it's just a calculator exercise. So 0.275 times 0.725 plus 0.231 times 0.769. All right, so that's all the stuff in parentheses. And then we're going to multiply that by 1.645 squared divided by 0.02 squared. And there it is, huge, 2,550.523273. So we would round up and get 2551. And then the other one, 0.5 times 1.645 squared divided by 0.02 squared. And this I typed in wrong, divided by, there we go, even much larger. So 3382, and so we would round this one up to 3,383. Right, so you need a very large sample size, and so both of these are going to be N1 and N2. So you set both sample sizes to that. Determining the sample size that you need to achieve a certain margin of error.